ei naught plus er naught by eta 2 cos of theta t. Arrange the terms around. Bring ei naught terms to one side. I get ei naught cos of theta I by eta 1 minus cos of theta t by eta 2 is equal to er naught cos of theta t by eta 2, and when I bring it there it becomes plus cos of theta I by eta 1. So it's telling me by er naught by ei naught r, which would be the reflection coefficient, just arrange these terms around. It would be eta 2 cos of theta I minus eta 1 cos of theta t by eta 2 cos of theta I plus eta 1 cos of theta t. Good way to remember is medium 2 property multiplied by angle in 1 minus medium 1 property multiplied by angle in 2, medium 2. Similarly, once I substitute this, what you notice here from that equation is et naught is now ei naught plus r times ei naught. So you get the same expression we had gotten before, that my transmission is dependent upon 1 plus r. So this is 1 plus r ei naught. So if I was calculating my transmission coefficient, which is e t naught by ei naught, this turns out to be exactly what we had seen before, 1 plus r, and would be 2 eta 2 cos of theta I by eta 2 cos of theta I plus eta 1 cos of theta t. Let's look at the reflection coefficient. My reflection coefficient R is going to be medium 2 property, eta 2 in medium 2, cos of theta I minus eta 1 cos of theta t divided by eta 2 cos of theta I plus eta 1 cos of theta t. Will this reflection ever go to 0 with any angle? At any angle? Well, if the reflection has to go to 0, eta 2 cos of theta I should be equal to eta 1 cos of theta t. Eta 2 we know is material mu 2 by epsilon 2, just writing it in generally, and cos of theta I can write because my function is in sine form, 1 minus sine squared theta I. My Snell's law is in sine form, so I better convert it back into sine. Eta 1 would be square root of mu naught by epsilon 1, square root of 1 minus sine square theta t. So far I have written it generally, but if mu 1 is equal to mu 2 is equal to mu naught, then this would cancel out, and what I would be left with would be 1 minus sine square theta I by epsilon 2 has to be equal to 1 minus sine square theta t by epsilon 2, by epsilon 1. And I can turn things around. I will get square root of epsilon 1, 1 minus sine square theta I is equal to square root of epsilon 2, 1 minus sine square theta t. Open it up, I get epsilon 1, 1 minus sine square theta I is epsilon 2, 1 minus sine square theta t, which is epsilon 1 minus epsilon 1, or let me just make it slightly easier, epsilon naught relative permittivity in 1 minus sine square theta I is epsilon naught epsilon r2, 1 minus sine square theta t. This cancels out. I have epsilon r1 minus epsilon r1 again. Remember, epsilon r1 is square root of epsilon r1 is n1, refractive index in medium 1. So epsilon r1 is n1 square. So I get n1 square sine square theta I is equal to epsilon r2 minus n2 square sine square theta t. But Snell's law says n1 sine theta I is equal to n2 sine theta t. So these terms are equal and they can cancel out, which is telling me epsilon r should be equal to epsilon r2, which is not true. So if I take a look at this reflection, and I am in non-mediums, this term over here can never be zero. For S polarization, there will always be reflection for every angle of theta I. Any angle of theta I go to, there would be always some reflection. If I was going to be plotting the reflection term versus theta I would have a term which would normally go something like that. It would start slowly and then it will start to increase as theta I is increased. It will normally go something like that. I give you a problem to just compute and appreciate this. Just take silicon, for example, and the calculate the angle, calculate the reflection as you go to different angles for a silicon wafer. But for S polarization, if the medium is not magnetic, if mu1 is equal to mu2 is equal to mu naught, there would always be reflection which would happen. Jaya, how much time do we have?
If you want, you can continue, sir, no problem.
I know, I mean, either we can stop now and then, because now we can do the p-polarization, but if I start the p-polarization, it'll take me at least half an hour.
Okay, sir, you continue in the next class.
Or we can do it tomorrow and we finish it tomorrow.
Yes.
All right. So tomorrow then what we'll do, so this is S polarization. Tomorrow what we'll do is we will calculate the same reflectivity when the electric field is coming in plane. The electric field is parallel in plane of the in the plane connect of that term. So the electric field is coming here. So there is going to be an electric field component which is parallel and an electric field component which is vertical, which is going to hit it normally. So it has to follow two boundary conditions. And what we are going to see is that the reflection for that is actually going to decrease, and there is going to be an angle where the reflection is going to be 0, and then it is going to increase, and as the angle is increasing it is going to approach the same value here. This angle is called a Brewster angle, and is theta b. You're going to see that this is the reflection for S polarization which we calculated today. We're going to get a reflection for P polarization which is going to be like that. It is going, as you increase the angle from 0 degrees, it is first going to decrease, and it is going to keep on decreasing till it hits an absolute value of 0, and then it starts to increase. So now if you think about it, if you're going to a water body or an ocean, let's say I have some water body here. You have sunlight coming in. Sunlight is randomly polarized, means sunlight has a component here and a component of electric field in this direction too. Both these electric field components exist. If sunlight is hitting at an angle, then this, if it is hitting close to the Brewster angle, then this value here, this value will not have any reflections. This will just transmit forward, and what you would get in the reflection term would just be your S polarization. Only electric field coming vertically would be reflected, and in transmission you'll have both S and P. So if you are sitting here now and you put a polarizer in front of you, what would happen is, if the polarizer is 90 degrees to your incoming light, if you're rejecting it, what would now happen is you would not see this reflection. You would reduce the glare. And that's why people ask you to wear polarization glasses anytime you have lot of oblique incidences. Anytime you're going skiing, for example, you get lot of oblique incidences of the sunlight, and in order to reduce the glare, in order to reduce that reflection which could actually hurt your eyes quite heavily, you wear polarized glasses. Why do the polarized glasses work? Because the reflection which is coming back at you is coming back only with electric field in one direction. So if you put a polarizer which opposes that electric field, you can reject it out and you can save your eyes. That's what we will do tomorrow. And with that, I think there's only one small topic left. I think I should be able to finish that topic tomorrow too. Else we'll finish that topic on Monday, and then we will just do problems after that. Jia?
Yes, sir. Yes, I will continue the same way.
All right. So we'll take the P polarization tomorrow.